Hi, my name is Shivani and this is my Lab 2 video. The purpose of this experiment is to observe the motion of an object drop from rest, falling straight down, and then to compare observations to a computational model. These are the table of contents and the topics we will be discussing. Part 1. Background information. In this experiment, it is necessary to consider Newton's second law, specifically the formula for V final. It is important to remember that with a free-falling object, the initial velocity is 0 meters per second, so the formula for final velocity will be the force divided by mass multiplied by time. Force will be calculated, since it is a falling object affected by Earth, by multiplying mass and 9.8 newtons, aka gravitational force. Here's the video of the observational data. A candy wrapped in plastic is dropped. In pink is the axis. The tilt in the video is accounted for. In blue is the calibration stick, which serves as a size reference. The red dots represent the center of mass of the candy throughout the video. In the tracker, it is important to switch the data on the y-axis from the x position to the y position, since the motion of the object is in the negative y direction. For the computational model, there are some steps that needed to be initialized. First, the mass of the candy was 0.015 kilograms. Second, the starting position and starting velocity were both to be set to vectors of 0. Next, the rest of the data remains unchanged, but it is important to note that the drag force is 0 in this model and the gravity is 9.8 newtons. W represents the formula used to replicate the falling of the ball. The equations boxed in yellow serve to represent Newton's second law. This was the resulting graph from the computational data, which is represented in blue, while the observational data is represented in orange. In the next part of the experiment, we change the code to account for drag. Fd represents drag force, which is equal to negative b multiplied by the velocity squared. The b value is the magnitude of drag force. In order to find drag force, numbers were tested until the final position in the computational model of the drag force is equal to the final position of the observational model. In this case, our magnitude of drag force was negative 0.008. The gray line represents the computational model that accounts for drag. You can see that from the blue line, aka the original computational model, to the gray line is a lot closer to the observational data in orange. By counting the drag force, the computational data and the observational data end near the same final position. The computational model with the drag force is a better simulation and representation of the observational data. In our first discussion question, we must examine the velocity versus time for each model. Which model predicts terminal velocity? Terminal velocity is the constant velocity that a free-falling object will eventually achieve after some time. In both models, the velocity changes over time as it increases the closer it gets to the ground. Both will reach a terminal velocity, but with the drag force, it will take more time. In the second question, imagine that the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? I changed the initial velocity in the code to be a non-zero value to represent this problem. With a starting velocity of greater than 0, the yellow line shows that the object would have reached the ground a lot faster. Moreover, there is less of a slope and the velocity is more constant, as the velocity reaches terminal velocity a lot sooner than when the starting velocity is greater than 0.